Hey everybody, how you doing today? Hope you're doing well. Alrighty, looks like everybody got the midterm in. Hopefully that went well for you. So I was going to go over it real quick if anyone was interested, at least for the long answer style questions. The quiz questions I don't think you'd have a lot of questions about, but it was just pulling them randomly out of the test bank essentially for those. So hey Trumpet Man, how you doing today? All right, yeah, hope you got your coffee. So we're moving on to Chapter 8, Lists and Dictionaries, but we can talk about those long answer questions if you want, and then I'll be working on getting all those graded for you this coming week. And that should be pretty good. Let's see, let me pull this up here. Come on, Candace. There we go. Yeah, there was no quiz for strings because we had the midterm coming up, so I wasn't going to bother with that. We'll pick up the quizzes again. Starting this week with lists and dictionaries, we'll come back and do quizzes for those chapters as well. Let me grab this. Yeah, awesome. Sweet. Yeah, I had a schedule. Awesome. And then we've got our third individual project coming up this week we want to look at as well. All right, so we've done projects 1 and 2. All right, so we're going to pick up project 3 this week, and then double check how that works in our schedule here. We should be able to get project 3 and project 4 in before the final project. Let me double check our calendar here. Let's see. Yes, we do lists and dictionaries these 2 weeks, and then pick up another project. Oh, we're not gonna have time. This being on the 13th was not ideal. So I'd like to do the final project this week, so we've got enough time to work on it here. That doesn't give us a lot of time. I wanted to do project 3 and 4, but I'm not sure that's going to happen. So maybe we'll just do one more individual project here. So just the 3 projects. So we do one Thursday that gets us in by this week. That Thursday, yeah. So let's do that. We'll do one last individual project. We'll talk about it on Thursday for project 3, covering lists and dictionaries. Classes would be useful, but not required for it. I think it'll make life a little easier, but not, not. I mean, we'll look at designing it with classes as well, but you can do it with just straight dictionaries for this one here. And then come week 12, we'll talk about our final project that we'll pick up for the rest of the semester. Then we've got that week, 1, 2, 3 weeks. Oh, that's not even a lot of time. Yes, a little bit of time over. I mean, Thanksgiving is mostly just the Thursday, right? So it won't feel too bad if you work on it on the Tuesday time. And we don't even have lab on that Monday either, which is weird. So there's no lab that week. So we'll do a lab on files come 11/29. And then we don't believe there's a lab. Yeah, there's no lab after 12/9 because the semester's done. Right, on 12/9. Let's take a look at the calendar. Yeah, so the 13th is the final exam slot, so there'll be no lab that week. So we'll just have the labs the 29th and the 6th after Thanksgiving. Okay, so I think that'll be our plan. So we'll do one last individual project come Thursday, have we do by this week. And then, we can even start the final project that week then too, to give you a little extra time on it. So if we started this, that Thursday, after we talk about modules on 11/11, that'll work out better. Get a little extra time on it. Okay, awesome. So do you want to talk about the long answer questions on the midterm, or skip them? I can do either. Totally up to you folks. Like looks like it's just you in chat here, Trumpet. Must not. Okay, cool. Yeah, hopefully that went well. So not too much stress there. So lists and dictionaries. And I'm not fond of time-bound exams at all. I've never. I mean, yes, there are time limits when it comes to programming something, but no one ever says, "Hey, sit down, do this in the next 2 hours," or and that's it. Rarely. I guess if something breaks, and it's a big issue, but most of the time we're not under insane time pressure, like, hey, sit down, do this thing. So they're not really a good measure of if you can get work done. Generally in the software industry, right, if you're meeting your objectives, you're getting the work done, which is great. And then, ideally it takes about 40 hours a week or so to do that, and it's a full-time job, but sometimes it takes you more, sometimes it takes you less, and generally it works out, depending on your organization. All right, so we're going to talk about lists and dictionaries. Let me grab that Zybooks chapter here, make sure I'm not forgetting anything as we go. Yeah, and hopefully they matched real well off the midterm practice. I mean, it's slightly different, but similar vein of questions, similar style. So I'm hoping everyone got 100%. That would be ideal. And we can go from there. All right, so we've done a little bit with lists and dictionaries already. We're going to go a little deeper here as we go and look at some other cool things we can do with lists and with dictionaries. So far we've added to them, right? Mostly all we did and checked if something was in it. I think we looked at removing a little bit, but not so much. I mean, for our purposes, we haven't had to remove anything. And we looked a little bit at this list slicing. So I've had a bunch of numbers. I said, hey, was my list of like 1, 2, 3, 4, 5 here, right? We know we have indexes 0, 1, 2, 3, and 4. So when we loop through, we can loop with a for list or using by index, right? And if we loop with a for loop, like if they say for number in numbers, if I were to change number, right, it doesn't change it inside the list. Number plus equals 10, and then print the number. And when we're done, if I print the numbers list, here nothing changes, right? Because this is a read-only, essentially. That's our read-only loop. Right? We give this a run. We'll see we get 11, 12, 13, 14, 15, but when we're done, our list is still 1, 2, 3, 4, 5. So nothing changed. Now, if we wanted to actually change the numbers, though, let's do another loop here. We can say for index in range in the length of the numbers, right? And this will give me all the index values, because when we're ranging, right, we're going to start at 0, and we're going to go up to, but not including the number we range to, which is perfect, because the length of 5 means I have indexes 0 through 4. So I could say numbers at index of, or index of index, right? Now we could then plus equal 10, and print numbers at index. And then when we're done, if we print out the numbers list, it's going to have been modified, because we changed it at its location in memory, right? It's not a read-only loop here, because we're modifying them in place here. Right? And we looked at if you pass a list to a function, we can modify the values inside the list here. So if you write a function like, I don't know, print values given some list, and we could say even both of these would be a read-only again, or we could modify them in place. What we can't do though is say some list equals a new list like 11, 12, 13, 14. 15. Oh, let's go back to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then print some list, right? So then if we give our list to our print values, so we call print values given our numbers list, and then we print out our numbers list, remember it's not going to have changed. Reassigning it here only reassigns it the value in the function. Right? It's not going to change the numbers variable down here because we've passed it the reference to where this is stored in memory. We said, oh, you no longer point there, you point over in this location. So it's kind of a funky thing when we're passing objects and values that reference memory addresses, really. It's essentially what's happening here. So when we run and we create a list, we tell Python, hey, I need a place to store a bunch of integers, right? And so it asks the operating system. The operating system says, sure, you can have x32fb. Here's a hexadecimal memory address. You go store your numbers here. 1, 2, 3, 4, and 5. Sure, go for it. We store them here. No problem. If we pass this list, so this was our numbers. Here, if we pass this to a function, inside of our function here, now the function has this sum list, points to the same location, still points to this x32fb, right? So if we change it, we say, hey, sum list equals something else, equals a new list. Python says, oh, you need a new memory address. Let's put this at x92fa. Right, so now sum list doesn't point here anymore. That's all canceled off. It points over here. So we haven't changed the original numbers list. Right, it still lives in this location in memory, even though we've passed it to the function as sum list. So you got to be a little bit careful. If you want someone to have access to your values, but not to be able to change it, right? Because we could change it by index value. We could change what's stored at the memory address by index value. You can pass them a copy of your list. So this means the function change the values in place. If we wanted to pass them a copy instead, we can do that slicing notation like we looked at with strings. You give it the square braces and you say, okay, what start and what end, right? And really, if they both are optional, if you just give it a colon here, you get everything from start to end, a slice of start to end. And when you slice, you get a copy. So now if you pass a copy of the list, even if they go and change some values by index, they're not going to change my original numbers list here. So it's important to know that you are generating a new list with slicing. And again, you can say, hey, slice from index 2 to index 5, or with the stride, you can slice backwards and skip. You do all sorts of cool things with slicing that we've done before. Works the same way, right? We can do all of those. Yeah, so those are pretty good. Different ways we can work with lists. Some other methods in lists which are really fun. So if you say numbers dot, right? We've looked at append. We can add things. You can get the count of a certain number of things. You can insert at a given index. So if you want to put, hey, it belongs at index 0 or index 1 or index 2, we can put them in. You can remove an item. Right? If we say remove, you give it a value to remove. It'll remove the first instance of that value. So if you have duplicates in your list, it's only going to remove the first one that it sees. Pop will remove the last item in the list, or pop given an index will remove an item at a given index. So pop removes the last item. Numbers.pop given an index like 2 moves the item at index 2, or numbers.remove, say 1, moves the first value of 1 it finds. And remember, when we're dealing with a list, now if you take something out, it just kind of shrinks. Everything has to move down in place. Other fun things you can do with lists is you can sort them. Numbers.sort will sort your list. Ours was already sorted, so not super interesting. Or we could like numbers.reverse, nope, not caps lock. Numbers.reverse, right? We'll reverse the list and then sort it. We'll put it back in place, right? So we can sort it, or we could reverse it. Either way here, we can get items out. I'm sorry, you can get the index of an item. So we can say, hey, the index of 3 is equal to my numbers.index of 3. And it's going to give me the index of where that 3 is. Here. Let's print index of 3. Let's give that a shot real quick. We moved, we reversed, we sorted. Oops, uh-oh. X not in list. For remove X. Oh, we don't have a 1? Do I not have a 1 in my list? Print numbers. Oh, because I've got 11. That's why, 11. Let's remove 11. There we go. We changed it here. Oh, and now, I can't get a 3 because 3 doesn't exist in the list. So how about 13? Let's see if we get a 13 in the list here. We get a 13? Index of, oh, that should be 13. Why didn't it print anything? Oh, 13 is not in the list. Okay, it did fail. Oh, because we removed it, right? If we removed item at index 2, so how about 11? I'm naming this badly here now. I have bad named variable names. 11 is not in the list either. Oh, because we removed 11. All right, let's try 12. Maybe we'll have a 12. One of these numbers we'll have in our list here. All right, so it's at index 0. Just different ways we can interact with the list, given all these cool methods. So for iterating over a list, right, we've done the for item as a read-only. We've done the index value as something else. There's also enumerate, which is fun. Yeah, eventually we'll find a number in the list. So if you want to, we can say for index and value in enumerate numbers. And we could print, let's say index colon value. So it'll tell us the index and the value of what, I should have done this first so I could see what's in the list. So we have at index 0 there's a 12, and index 1 there's a 14. That's all we have left in our list. So enumerate is handy in that it'll give you both the index and the value. Right? We're just like a for in a range only gives you the index, and if you want the values out, again, you have to go ask for it by value. This value bit here though is still read only. So the value is still a copy. Essentially, it's a read only. If you change value, it's not going to change it inside the list. So you always need to change things using an index if you want to change it inside the list. Let's see. Yep, you can do max, you can do min, you can do sum. The any and all are a little bit funny. It just means if anything is true, or if all things are true. And Python's a little funny in that 0 is false, and any other number than 0 is true. So it's a little bit funky when you're dealing with numbers to do any and all. All right, cool. Some other things with lists. Max, finding min. Yeah, all right, so a nested list is a list within a list, a two-dimensional list. This is where lists get fun. Did we look at these before? A two-dimensional list where we had a list of lists, where we had rows and columns? I feel like we did that briefly. Right, so if I said, here's my two-dimensional list equals a list here of lists, and we could give it some values like 0, 1, and 2, and then another list of like 1, 2, and 3, and then another list of like 2, 3, and 4 or something. So, okay, so usually we would write these out. I'm fond of putting them in this kind of format here. Now, usually Python's not happy with all these extra spaces, but when you do a two-dimensional lists, it kind of understands, yeah, we're going to put some extra spaces in here, and it's okay with it. So if you just print two-dimensional list here, it's going to look kind of ugly. We just get it all flattened out one at a time. If you want to print each row at a time, we could say like for row in two-dimensional list here, you print the row. Remember, row is itself a list here, so row has indexes as well. So if you just print the row out, we get a list, a list, and a list. Let's just keep the numbers going. We'll do 3, 4, 5, 9, 8, and 7. How about that? So if you wanted to do, you could do a second loop then. We could say for column, really it's, I don't know, like value in row, right? You could print the value, and then you can change that ending character, right, to say, hey, let's just end with a space afterwards. So we can print every value separated by spaces here. Then we could just print a new line character to go down after every row. So this is going to get rid of those square braces here. I guess we could even do, I don't think we want commas though. We just do it this way. So we get the values out here, right? One value at a time, because row is another list, and we're saying for each list in the list of lists. So you think of them as row and column. So there's a row index and a column index. If you wanted to say, hey, this is like row index 1, column index 1, we could say, right? So we could say my two-dimensional list, index of, so what row, index 1, what column index, index 1. Right, so the first list notation says, hey, give me row 1, index 1, and the next one says, okay, of row index 1, give me column index 1. So give me 1, 1. Should be the 4 here, right, because that's at 1, 1. So it's a little bit funny. Remember, in math land, right, 0, 0 is like the origin in the center. It doesn't work like that when we're dealing with rows and two-dimensional lists. So for us here, we have this list of lists, right, and each one of these is a list. Each one of these is a list. Each one of these is a list. So this is row 0, 0, row 1, row 2, right? And we get column 0, column 1, and column 2. It's a 1. That's a 0. Right? So you kind of imagine, hey, Aiden, thanks for coming on by. Right? Each one of these is at a given row and column by index. So this is 0, 0. This is 0, 1. This is 0, 2. 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, and 2, 2. Right? So we get row and column indexes here for this notation. That makes sense with a two-dimensional list. It's a list of lists. So you can get out the different values. You can get 3 dimensions, 4 dimensions, 5 dimensions. You can go nuts if you want. Honestly, beyond 2, and you probably want a different approach because you've just gone too far. People are good at thinking in grids. We're pretty good at row and column. Once you add like a depth there for that 3rd dimension, people's heads start to spin. And if you want to do a 4th dimension, nobody can visualize it. It just makes no sense anymore. But we could play a little tic-tac-toe game if we wanted, right? So if we make a little tic-tac-toe board, we'll just call it a board. How about that? Equals a list here. And inside of that list, then we'll have a list where, let's just do a bunch of spaces to start. Space and space. That's our first one here. And then we'll add, I'm going to bring that down a line actually. So that's the first one, that's the second one, that's the third one. And that ends our list there. Let me bring that over one, tab these ones in. I like everything to line up real nice and pretty, right? And maybe that one can hang out there, I don't know. So if we start with an empty board here, right, we could ask them, hey, whose turn is it? And so, I don't know, we'll say player's turn, or whose turn? Who turn? Whose turn? Whose turn? Is that English? We'll start with X's here. And then we'll ask them. We'll say, okay, where do you want to go? We can print out the board here. So why don't we make a little method? We can just print the board. That's okay. If we just hit, oh no, we want to print it a little bit nicer here. So we'll make a method for print board. Print board. Given a board. And we'll say for row in board, we'll just print the row. Again, we can deal with the little braces here. It's not too bad. Won't be too ugly here. Okay, so we can print the board, or I'll call print board, given the board, right? And it'll print it for us. And then we'll say, I don't know, print its little formatted string, whose turn, X's turn, and we'll ask them where do they want to go, right? So we can ask them, so for a row and a column, so a row can be, and actually we can do both, right? If you do the split, right, you can do row and column, equals a split of an input of enter the row column to place your mark here. Nope, sorry, input dot split. Like space separated, I don't know, separated like 1, 1. Sure. I don't know, that seems like a terrible prompt, but that's okay. We'll split it here and we'll get those 2 values out. So if we have 2 values when we split, we'll get row and column. Right? And then we can take the board, index of the integer value of the row, the integer value of the column, right? And we can assign it a value of whose turn, right? And then we can say whose turn then equals O. An O, there's an O, that's an O. We can print the board, right? And again, you know, this is getting a little bit ugly here, but we could clean this up as we go. We can kind of interact with it. All right, so we get, here's our board. Where do you want to go for X? Where should we put our X? X in the center. All right, so that's 1, 1. Oh, goodness. Print board. Oh, I forgot to call board. I didn't give it the board. Let's try that one more time. Corner. Oh, my goodness. I don't know how to type, friends. 1, 1. No, you always want to go in the center. Center, Aiden. All right, so 1, 1. All right, and then, you know, we'll have to say whose turn is it again. So here, let's clean this up. We can do this a little bit better here. So what we want to do then is we want to keep on playing while the game is not over, right? So let's keep on going while its game is not over, right? So while not game over, given the board, we'll print the board. We'll say it's blank's turn, and then we're going to change whose turn. So whose turn is going to equal. Now, we can do one of these crazy ternary expressions if you want here, because they're cute. We could say, hey, it's X's turn if whose turn is equal to O. Otherwise, it's O's turn. Does that make any sense as a ternary expression? No, is that a question? No. Else. There we go. Getting my languages mixed up here. I'm sorry. So if whose turn is O, it becomes X's turn. X. They'll do capitals here, right? Otherwise, it's O's turn. Right? If it was O's, it flips to X. If it was not O, then it becomes O's turn. Center is easiest to defend. I mean, you're not ever going to lose tic-tac-toe if you know how to play, right? It's impossible. Oh, not. My goodness. Well, not game over. We have to define a game over method. We'll define game over given a board. Now, there's a couple ways that you can get a game over. Hey, Dodo, thanks for coming on by. Right? A couple ways that you could have a game over in tic-tac-toe. First, there's a cats game, right? If there are no spaces, then the game is over. Right? So we can say, you know, cats game, right? So we're gonna, hey, that's so cool. Awesome. I'm glad they're doing some fun lectures. So we have a couple ways, right? X can win, O can win, or the game could be over. Right? That's pretty simple for that. You know, it's a little bit tricky to define some of those, but that's okay. We want to break this up. We want to do some of that functional decomposition. I'm a big fan of that. So for whether or not the game is over, let's check. We can say we're going to return a combination of is cat's game given the board, right? Or I don't know, x1 given the board, or o1 given the board. So if you give me a board here, I can tell you if it's a cat's game, or if x1, or if o1, right? Either of those will work, or I guess any player one, maybe? A player one? How about that? A player one. We'll just say any player one, and we can figure that out after we go. We need more functions then. So is cat's game, given a board, needs to return a true or false. So we can say for row in board, if there's a space in the row, return false. Right? If I found a space, the game's not over yet. If I've gone through every row on the board and I haven't returned a false, I can say true, we must have be a cat's game. We must have tied. Right? And then for a player one, define player one, given a board here, we got a couple ways. Now, really, if it's X's or O's, I don't really care. I just need to know if a single player won. So we can do by row, we can do by column, and we can do either diagonal. I mean, either one of those will win here. So I can break those out and do them separately, right? That's, I think, an easier way of kind of breaking the problem down. So we can return a horizontal win, or win by row, given the board, or win by column, given the board, or win by diagonal, given the board, right? Again, we're just breaking this down. That's a big problem to solve, so let's solve it in smaller problems. So win by row, given the board. So to win by row, we're going to look at the row here, and we're going to see if all three match, right? If it's an X or an O, I don't care. So we're going to say for row in board, if row index 0 does not equal a space, right? If it's not a space, if it's a space, obviously they didn't win, and row of 0 equals row at index 1, and row at 0 equals row at index 2. Posture check. Thank you so much, Trumpet Man. Yes, let me get out my backboard here, because I am slouching. So for a given row, right, if it's not a space in the first character, and then the first character matches the second, and the second matches the third, you can return true. We found a win. We found a win. If we've gone through every row and we haven't returned a true, then no one won by row. That's a false. Oh yeah, Dodo. The dealing with floating point numbers is surprisingly bad. Surprisingly bad. It's, I don't know. It's just what it is. So, thankfully, we don't need insane amounts of precision for most things in the world, right? Like if I always like this fun example here. I don't know, how many digits of pi we need on the moon? Or maybe it was I forget what it was. There was some interesting article here. Yeah, the Jet Propulsion Lab here from NASA said, you know, we know pi to lots and lots and lots of digits here, but for interplanetary navigation, we use 1, 2, 3, 4, 5, 6, 7, 8, 9. That's like 15 digits, right? 15 digits of pi can get us within 1.5 inches. Here, at 78 billion miles away. So, like for interstellar navigation, interplanetary navigation, right, we can get 78 billion miles within a couple inches here with only 15 digits of pi. So even if we lose like a little bit here at the end, probably okay. I don't know. I'm spoiled in the fact that it's not really a problem for me very often. All right, so winning by row, right? Easy. Done, right? We're going to break down problem by problem by problem. So let's define win by column for a board. Now, this is the exact same thing here, but I need to go by column index. I need column index 0, column index 1, column index 2. So I'm going to say for column index in range 3, right, which will give me 0, 1, and 2, right? I'm going to say if my board at row 0, column index. Column index. Right, so always row 0 to start if it's not equal to a space, right? And my board, now I'm going to look at the next row, same column index. So row 1, same column index, right? Oh, I'm sorry, that one does equal that. If that one equals that one, right? So if it's not a space and it equals the next row, right? And it equals the third row. Return true. If we looked at every column, we'll return false. And we haven't returned a true, we can return false. Did that not tab out right? Why is that not? Yes. All right. You should be able to bring these down. Oh, okay, I'm sorry. I forgot our slash. So to bring the logical endings down, you have to have this weird slash character. It's fine. So we'll say, okay, if row 0 for this column is not empty, and row 0 matches row 1 at that column, and row 0 matches row 2 at that column, we can return true. And we're going to check all 3 columns doing this range here. Right? Okay, and then winning by a diagonal, define win by diagonal, given a board. Now, this one you know, we could do some funky sort of ranging here, but really it's just, you know, 0, 0, 1, 1, and 2, 2, right? For our 0, 0, 1, 1, and 2, 2, or 2, 0, 1, 1, and 0, 2, right? Either one. So we're going to say if board at 0, 0 doesn't, actually we can check 1, 1, 1, 1 does not equal a space, right? Because that's our first case here. Because either one we're going to pass through 1, 1. So that one can't be a space to have a win by a diagonal. Not equal space. And then this one equals board at 0, 0. And that one equals board at 2, 2. Right? So 1, 1 matches 0, 0, and 1, 1 matches 2, 2. Hey, thanks so much, Aiden. Thanks for dropping by. Right, so that's our diagonal. This direction, 0, 0, 1, 1, 2, 2. They match. Right? So that one is one case here. Then we can get fancy if we want. We could say this thing here, right? Or, I need my backslash there. Let's do the other ones here. Board at 1, 1 matches 2, 0, and board at 1, 1 matches 0, 2. Right? 1, 1 matches 0, 2, and 1, 1 matches 2, 0. So as long as the middle's not empty, and this or this. Right? And, you know, I can force this order of operations. It should be fine here with our ands and ors, but it never hurts to give extra order of operations here. Right? So this now, we're saying, okay, if it's not empty and it matches the other corners, or it matches the other corners, right? Either sets of corners, we're going to return true. Else, otherwise, if we haven't, then we can return false. Now, this is kind of ugly here because this is already a Boolean expression here. So I can just simply say return that, because this is a true or false statement here. Right? This will be true or it will be false. Why does it not like extra spaces here? I like extra spaces here. Sad the style guidelines don't. Is that redundant at that point? What does it not like? I don't know what that one is. Why is it complaining about my or? All right, it just didn't like it on a separate line there. Now it's too long. I know it was too long. That's what I was doing here, friend. Oh, it wants it lined up like that? Sure. Whatever. All right, so but that's our win by diagonal, right? We can win either direction by diagonal that way. How's that sound? So for game over, it's if it's cat's game over player one. If it's a player one, they win by row, by column, or diagonal, right? We're just breaking all these down over and over and over again here. We're going to keep on playing while the game's not over. It's whoever's turn. We'll ask for a row and a column. But now we want to make sure that we don't assign it on top of something here. Right? So we need to check here then, right? We can say while this equals a space, we'll print you can't go there. Oh, two quotes. You can't go there. Right? And then ask them again. Sure. Then we'll assign it to whose turn, and then we'll change whose turn it is, and we'll keep on printing. Right? When this loop is done, then we'll print game over. Maybe we print the board one last time. Right? Sure. Can we try that? I think we've got a tic-tac-toe working now, right? Let's give it a try. Okay. It's X's turn. Where do we want to go? Trumpet, you said 0, 2 before, right? We can go to 0, 2. Uh-oh, we can't go there. Oops. Well, it does not equal a space. I had that backwards. If it's not a space, we can't go there. My mistake. Let me retry this one more time. Let's give that a run. Stop and run. Okay. Trumpet, you want a 0, 2? 0, 2. All right, so we put an X at 0, 2. We're in the corner. It's O's turn. Where should O go? Right? O has to go in the middle, right, to defend. Otherwise, it's game over. We got to go at 1, 1. All right, I'll be O's, you be X's, Trumpet Man. Or Bayman, you can play too. Bayu, Bayound? I don't know how to say your handle, I'm sorry. Can I just call you Bay? All right, we got our tic-tac-toe going here. Give it a try. Two. All right, you're going to 2-2. All right, I got to block you here, so I'm going to row 1, column 2. There we go. There we go. You're blocked. This will be a cat's game real quick here. Real quick here. Where are you going? You want to go to 0-0? You going to let me win? All right, go to 0-0. All right, I'll go to 1-0 and I win. Game over, sucker. O's win. You handed it to me. My guy, my dude. Uh-oh. You want to try again? A rematch? We'll try it again. It's okay. It's all right. Where do you want to go? I'll let you start. One more. And then Bay, you want next? All right, 1-1. You got it. All right, you're in the middle. I got to pick a corner, and then I'll go 0-0. Done. Easy. Let's go. My kids refuse to play tic-tac-toe with me anymore because they never win. 2-2. All right, sure. Okay. Yeah, that's fine. That's no problem there. So I just got to block you, right? I don't even have to block you. I just need to make you go somewhere. So I'll go 0-2 here. There we go. There we go. Bring it on. Where you going, Bay? Zero, 1. All right, you're going 0-1. All right, you're going to block me, so then I got to block you. So I'm going 2-1. Okay, easy. All right, you got one other chance to win, and I'm going to block you either direction. This is good. We'll get our cats game. Make sure it stops. All right, 1-0. You got it. All right, so I'm going to go 1-2 to block you. All you got left is 2-0. Game over, cats game. The champion is undefeated here. Undefeated. All right, give me half a minute here, guys. Sorry, I need to... daughter's having some trouble hopping on Zoom. Just a minute here. I'll be right back. What's up, Journey?
The meeting isn't working.
Hey, folks. Sorry, that took longer than I expected. Zoom is not taking the password, and this is why I hate Zoom. Like, it worked on my phone, but not on the laptop, because reasons, and that was stupid. Alright, so, sorry about that. We had some fun with lists, right? Made our little tic-tac-toe game. But again, that's this whole idea, right? We're looping through by row and by column with two-dimensional lists here, having a little bit of fun with them. Changing values. Yep. Now, one thing you want to be careful of as well. Never heard a more accurate description of Zoom. I don't. It's happened before too, which is super weird. Like, it's the same room she uses every week, and every so often it just won't take the password, but a different device will work. So, like, I don't know. I uninstalled Zoom, reinstalled Zoom. I kind of know how computers work, and I feel like something's going wrong if I can't make it work here. All right, yeah, let's do a quick little example here. So when we're looping through numbers here, we'll say, I'll just make our numbers list again here. Like 1, 2, 3, 4, 5, 6, 7, 6, 7, 8. Here, you know what? Let's say you can cheat. We'll just do this. We'll do is a list of range. Let's go 1 to 11 to get the numbers 1 through 10 here. So a range itself is not technically a list, right? But you can hand it to list to make it into a list, right? And I can print numbers. And then we'll say for number in numbers, if number modulus 2 equals 0, let's take my numbers and we want to remove number. Okay, so let's try and remove all the even numbers here. Let's print numbers. Let's see if that works for us. Oh, we got to play tic-tac-toe. All right, 0, 0, 1, 1, 0, 1, 2, 2, and 0, 2. There we go, x1. So now we went through 1, 2, 3, 4, 5, 6, 7, 8, and 10. Great. We're going to loop through the numbers. Number of numbers. Let's remove the number. When we're done, we print it back out. We get 1, 3, 5, 7, 9. Okay, that worked out here, right? It's not too bad. It removed it here. Let's see. Actually, it shouldn't have worked. What did I do wrong here? Why did that work? Huh. Remove the number. Why? Goodness. Why did that work? That was a problem. So generally, you don't want to remove items in a list you're looping through. That can cause all sorts of weird problems, but for some reason it worked. I'm really surprised. It actually did work. Just for fun, let's try and remove the odds here. Oh goodness, here let's just win. Oh goodness, it broke. Kind of want to skip over that, but that's okay. 0, 0, 1. I don't know how to type, friends. 0, 0, 1, 1, 0, 1, 2, 2, 0, 2. Okay, game over there. All right. So it did. It removed it. That's funky. Should not have done that. Why? Why is that working? It's supposed to break. Oh, goodness. Let's remove the number. Okay, you know, I think let's try it this way here. Let's try for index and range of the length of numbers. Here we go. And then if numbers at index mod 2 equals 1, let's remove numbers at the index. This will probably break now better. I think that's the idea. All right, 0, 0, 1, 1, 0, 1, 2, 2, 0, 2, game over. There we go. Now we broke it. Okay. Yeah, I wasn't ranging over the length properly. So if you range over the length of something here, and then you go remove from it, I used to have indexes 0 through 9 for all my values, right? For my 10 values here. I used to have indexes 0 through 9. As soon as I remove something, I no longer have an index there. Right, so if we watch this in debug mode, which is lots of fun here, so let's do this in debug. I put a breakpoint in and run it in debug mode. We can see the list is losing items, but the range doesn't change. Here, so we'll do 0, 0, we'll do 1, 1, we'll do 0, 1, we'll do 2, 2, we'll do 0, 2. Okay, now we hit a breakpoint. So we have our numbers list here. This is my numbers list. These are the values at the indexes. So we're going to step, and we're going to step, and we're going to remove the item. Now my length is only 9 here. We'll go through, don't remove, go through, right? So now we're currently at index of 4. Well, index of 4 is looking at the 9 already. I'm going to go remove the 9. Now index is 5. I don't have an index 5, and my program crashes. There is no 5, right? So looping through a list is bad, bad, bad form, right? Or modifying the list you're looping through is bad form, because it's going to break. Now, it worked when we were looping through using the for loop, because it was getting a copy out each time, and as we removed items, it's fine. We were still just taking the next item in the list. But even then, you can occasionally get into issues where things get skipped. So I think it was fine. Let's do this. Let's do, let's say, want to, before we do this one here. So this one is bad, right? I'm going to stop that debugging here. So this one will crash. I'm just going to comment it out because it crashes. So it will crash since we run out of indexes. We remove items. Right, so the length changes. Changing length is risky. That one's no good. So let's do this one though. Let's say for number in numbers, if number is greater than 5, greater than or equal to 5, how about that? Numbers.remove number. This one's going to break. Yeah, editing lists in your word scrambler, yeah, it doesn't go well. So now let's try and remove all the numbers greater than 5. 0, 0, 1, 1, 0, 1, 2, 2, 0, 2, I win. Here we go. Uh-oh. We tried to remove all the numbers greater than 5, but it didn't work. So what happens here is it's going to give you the next value, but as you remove one, the next value then gets skipped. Because so what happened, we used to have, let me do like a new page here. Oh no, my coffee. Well, crap. Friends, this is why you shouldn't keep stuff on your desk. Alright, not so bad, but it's a waste of good coffee, which is really sad. Really sad. I guess I should have just drank my coffee faster. Then I would have solved all my problems. Not having a good day today, friends. Apparently not having a good day. Okay, I think we're good. Oh, I didn't finish my muffin. Coffee. Okay. Wow. Totally pro streamer here. Pro streamer. Yeah, F, thank you. F's in chat. Just drink the rest of this. Okay. Anyway. So we had a list here, right? And we had numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9 in here. right? Or we had 10. We also had a 10. Okay, so we loop through, we say for number in number. And behind the scenes, it's keeping track of where it is. So it says, okay, currently on this one, then we're on this one, then we're on this one, then we're on this one. We get to 5, and we say, okay, if it's greater than or equal to 5, remove it. So we remove 5. What happens when you remove 5 is everything shifts down 1 to here. So then 6 gets put in its place, right? So we put 6 here. We took 5 out. 7 gets put here. 8 gets put here. 9 gets put here. 10 gets put here, and we just remove this thing on the end. So the next place we go to look is 7. You say, okay, 7's greater than 5, remove it. Remove 7. 8 gets put here. 9 gets put here. 10 gets put here. Remove those ones. So the next place we go look is 9. You say, okay, 9's bigger. Remove 9. Put 10 in its place. Nothing left. And then we're done looping through the list. So we got back out. We left 6, 8, and 9 or 6, 8, and 10 because we skipped them. That's why doing the odds and evens was working, because it was every other. It actually worked out for us. That was my mistake. That was a bad example. So this one fails because the items shift. So what you want to do instead then, you want to say for number in numbers slice. Give me a copy here. So I'm going to loop through all of the values in the original here as a copy form, so nothing changes. Then I can remove them from number here. Then when we print numbers, right, we'll actually get the right value out. Because now they're not going to shift underneath here. So looping through a copy prevents the items from shifting as we loop. So both ways you have to be careful. Right, so 0, 0, 1, 1, 1, 0, 1, 2, 2, 2, 0, 2. There we go. Right, now we can actually remove all the items because we're not going to do that skipping because we're looping through the copy. Right, and then the last thing we're going to talk about with lists here, before we move on to dictionaries, is list comprehensions. So just a shortcut here. People love shortcuts all the time. And we looked at one briefly last time. I was like, okay, this is the thing. We'll talk more about it later. So we say, I want my resulting list to equal, and then in list braces here, we give it one of those expressions. It's almost like a ternary expression, but it's a for loop. So we'll say, hey, I want the integer value of the number or number in input, enter a bunch of numbers, space separated, dot split. So this is crazy looking. So you give it something that's a collection, right? In this case, we're taking an input and splitting it on spaces. So here's a collection. Then what we're going to say, every item in that collection we're calling number, do this thing here on the left, and then turn it into a list. Right, so we print my resulting list is the integer values of those. So 0, 0, 1, 1, 0, 1, 2, 2, 0, 2. Enter a bunch of numbers space separated. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We get back out a list, but notice they're not strings. They're integer values. We could also do some silly stuff like, hey, integer like times 2. If you wanted to double all of them, right? So you can do any sort of single line notation here if you want. And you can do something with it. You can convert, you can input, you can do sums of things, you can do all sorts of fun stuff. So the book will take you through a couple examples in this. But common for us is doing this sort of list. And then if you want, you can even add an if expression, right? Which is crazy. We can say, well, if what? We can say, if the int of the number mod 2 equals 1. So only give me the odd numbers here, right? So you can throw in the if. The if is optional. Let's put this in a comment here. This is the expression. This is the item. This is the collection. And here's the optional if. Goodness. And you read it really funny here. But now we'll only get odd numbers out, right? Or we'll get our odd numbers doubled, actually, here, which is crazy. So we're going to double all the odd numbers. We'll get a bunch of evens again. but sure, why not? 1, 1, 0, 1, 2, 2, 0, 2. All right, a bunch of numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We're going to get 2, 6, 10, 14, 18. Did I miss a number here? No, that's 1 doubled, 3 doubled, 5 doubled, 7 doubled, 9 doubled. Yep, those look good. It's just a weird way to count. So list comprehensions are cool. It's the exact same thing as doing it in multiple steps, right? So it's just a single line version of, here's where let's get an, I don't know, series, user's input is equal to an input of enter a bunch of numbers, space separated. And then we can say for number in user's input dot split, we can split it for every number in there. If my number mod 2 is 1, then I'm going to need a list to put these in, right? So my new list is a list. Take my new list dot append we need that to be an integer value, right? So an int of the number here, right? Append the int of the number times 2. So this is going to do the exact same thing here, right? So 5 lines versus 1 line. This is why people like these list comprehensions, because you can do it in a single line. They're a little bit hard to read sometimes, but after you've read enough of them, you kind of understand this weird backwards flow, just like these ternary expressions, right? Where we did, hey, let's change the value. We'll set it to x if it's O, otherwise it's O. Right? Same idea. After you read enough of them, you kind of get used to it, and people love to do these in Python all the time. So we're in pretty good shape. It'll take some practice, and that's okay, right? No big deal here. One last thing with lists here. You can sort lists. So when you go to sort a list, right, there was my new list dot sort would sort my new list. If you want, you can have a sorted list equals sorted of my new list. And the difference here is this makes a new list. This modifies the existing list. So dot sort will sort the list you're asking it to sort. Sorted will make a new list from this list, so you can create a new list here then. That's all. And you can actually give it different sorts for minimums and maximums and reverse sort of things. You can reverse it. I never remember those, but you can always just call dot reverse afterwards anyway. So like you could sort and then reverse. Technically, you can do it all in one. With sorted, you can say, hey, reverse is true to do it in reverse, but that's all nice and well and good. Okay. Then the command line arguments is fun. You can look at those later. We're getting there. So chapter 8 is a big one here. We got all sorts of dictionaries to talk about on Thursday as well. So we'll leave dictionaries for Thursday. Okay? We'll call it a day here. Let me commit this stuff to GitHub. Thanks for hanging out today. Thanks for playing tic-tac-toe. And we'll go from there. Okay, folks? Let's see. Is there anybody we should go raid? Let's see who's around. Let me put on my ending screen here. It's a little easier. Stream ending. A dad joke. You got it. Actually was saving a couple. Oh, my daughter has my phone. Oh, my wife's just sent me one. So it turns out there's a new way that you can determine the gender of an ant. If you put an ant in water, if it sinks, it's a female. Right? Otherwise, it's a boy ant. That was a little bit of a stretch, but it was trying there. It's trying real hard. End burrows. Let's go do some chemistry stuff for fun. Why not? Let's go raid burrows. Let's go learn some chemistry. All right, folks. You take care. I will see you next time on Thursday. Everybody take care.